Hi everyone. Here we will present the work we have done on plan-aware resource allocation in serverless query processing. My name is Malay. I work with Alekh and Hiren on this. In serverless query processing, user specify the amount of resource that will be used by the query during execution time. It is hard to estimate the resource. If there is under allocation, job might be slow. If there are over allocation, resource user might end up wasting resources. Also, the amount of data processed by each query varies depending on the instances, and the amount of resource required by query during execution time varies also. Because of this, user might end up wasting resources. For long-running query, this is even worse because we observe as the job progresses, it uses less and less resources. Here is one skyline graph of one user query. We can see user initial allocation is way off the actual allocation. Also, as the job progresses, we see dip in the allocation, then it uses the user allocation, the usage of the allocation resources increases, then again dips, and so on. Because of these complex natures, in general, it is hard to estimate the resource required by a particular job, particular query. There are some work done in this area to produce better estimate. For example, looking at the query plan and considering the past history of the jobs, it tries to produce those estimates. But all these approaches does not look into the dynamic behavior of the query execution over time. They consider the execution as black box. In this paper, we introduce plan-aware resource allocation strategy. Here the picture represents our current architecture diagram. The blue lines and the blue rectangle represent the new workflow and component we added for plan-aware resource allocation strategy. The central component of this plan-aware resource allocation strategy is resource separ. Resource separ has access to the query plan generated by the query optimizer and the current execution statistics from the job manager. By looking at those two, resource separ can produce the future resource requirement. Job manager, by looking at the future requirement, it can give up the extra resources if the future requirement is less than the current requirement. It does so by sending messages to the job scheduler. Since we make the resource separ lightweight, conservative, and safe, it does not incur any performance impact on the overall query execution. So we can invoke resource separ frequently without seeing any delay in job latency. In the next slide, we'll see how By looking at query plan and the current job statistics, resource separ saves the resource usage of the query over time. Here we can see how the resource usage varies over time. Initially, resource separ look at the plan and calculate the peak requirement and update from 125 to 80. Job manager gives up the extra resources. As the job proceeds, resource separ constantly and periodically, resource separ gets invoked periodically, so it keep updating the new peak requirement and job manager keeps giving up the extra resources. The overall resource usage shape look like the red area. Without resource separ, entire rectangle represent the resource time resource usage resource time usage. With the resource separ, we can see how much resource time saved, which represents the white area under the rectangle. We also want to emphasize the fact that since we make the resource separ lightweight, conservative and safe, it does not incur any performance impact as well as does not cause any resource starvation due to under allocation. It is also transparent to the user. The next couple of slides will describe one greedy approach, one greedy implementation of Planaware resource allocation strategy. So finding the remaining peak resource requirement is equivalent to finding max vertex cuts in a DAG. We have added in detail in the paper. Here we will briefly go over the greedy implementation and then work through the example. Since finding max vertex cut in a DAG is not solvable in polynomial time, we introduce a heuristics. We convert the DAG to set of disjoint trees by tree-fi algorithm. Then find max vertex cut for each tree separately and sum them up. And if the new requirement is less than the current requirement, we give up the resource. We'll explain those two tree-fi algorithm and the remaining peak algorithm in the subsequent slides. The goal of the remaining peak algorithm is to find the max vertex cut for a tree. It does so by recursively traversing the child, calculating the remaining for each child, and then finding the max requirement of current node and sum of all child nodes. One of the major component of our plan-aware resource allocation strategy is treeification. We convert DAG to a set of disjoint trees so that we can run max cut in parallel, and also it become linear in terms of time complexity. In Microsoft scope terminology, we use spool operator as the operators or the nodes which have multiple consumers. When converting DAG to trees, we start from the output nodes, then look at the parent-child edges by reverse way. Whenever we encounter one spool operator, we remove one edge, we remove the edges except one. While selecting which edge, we choose the one to the consumer with higher in degree. In case of ties, we can select randomly. This process results in set of disjoint inverted trees. In this picture, we can see the DAG is broken into 3 trees represented by 3 different colors. In the next slide, we can see how our greedy algorithm works to calculate the overall resource requirement. As I mentioned in the previous slide, treeification results in 3 different trees represented by 3 different colors. Here, the number next to the node name within bracket are the number of tasks or processes in that stage or that node. Green number signifies completed task, orange running task, and gray tasks which are not scheduled yet. So to calculate the max vertex cut, we calculate max cut for each tree separately and then sum them up. For the first tree, we can see the max cut is 30, which is from stage 5. S1 and S2 is completed, so we don't use those numbers. Similarly, for second tree, the max cut is 50, third is also 50. The sum is 130, that will be the next resource requirement of this particular DAG. So this entire calculation is done just one pass DFS and done in linear time. So this is pretty fast, and also with this simple heuristic, it all shows huge improvement. We'll see later on our experiment result. We have randomly selected 154 jobs and run in our production cluster. In the right side, we can see the amount of savings we obtain for each job. Savings varies from 0 to 75%. Overall, there are 8.3% savings of cumulative resource usage. We have also done data analysis on our production clusters. We observed that we can have up to 19% savings of cumulative resource usage. That will translate to tens of millions of dollars in operating cost saving. In summary, we saw that the simple greedy implementation of plan-aware scheduling produce pretty, pretty good result. We can work on the better heuristics, and also we can think of more aggressive strategy. Like in our approach, we only look into the future peak resource usage, but we can also think of more conservative, more flexible approach of following the token usage curve. Thanks for listening.